about TensorFlow.
Thank you so much.
No problem. Okay, does that look good?
Yeah, perfect.
Awesome.
Good afternoon. It's a pleasure to be here, and I know it's late in the day, so we would try to keep it short and sweet at the same time. So, but typically, it's more like a narrative on building machine learning products and how you can leverage TensorFlow and the Google Cloud ecosystem. So I would downplay technicality and rather give a high-level narrative. So we kind of grasp the process of having a data product. Because when we talk about machine learning, a model, now from an applied perspective, not from a theoretical perspective, when it is applied in industry, a model in and of itself has no business value. So you must be deploying a product, and it's a product that actually makes money. And in the business world, from an industry perspective, that's what matters. So how can we leverage these tools to deploy products? When we talk about machine learning, or from an industry perspective, there are lots of facets. There are lots of things that go into deploying an ML product. And one thing we realize is that the model is just one component of that whole deployment product development pipeline. So we have to deal with issues like ingesting the data, doing a data health check, pre-processing the data, and all that kind of things. And how do you the analysis of the data set itself, and then the modeling comes in, and a couple of steps after the model, how do you productionalize the model, and so on and so forth. So those are other concerns that are part of the whole product deployment pipeline, for which the model is one component of. So Google Cloud Platform really, it comes with a lot of, it makes the whole ML modeling simple. Well, not that we use the word simpler, but it brings a certain efficiency to it because of the scalable and parallel tools of Google's compute infrastructures. So we're able to leverage that and speed up the time of model development, and also speed up the time of the other processes that goes into deploying this, that goes into preparing the ML pipeline. So if you, from the word go, ML modeling is a highly repetitive process. So if you're able to cut down the time you're spending running or test running or spot checking a particular algorithm from, say, a couple of hours to a couple of minutes, because you're leveraging GPUs and multi-core distributed processing, that's massive. And the cost, this will also cut down in the long run the cost it takes to get your own GPU and set it up, and otherwise you're not using it, especially when you're not running models every day. But if you use just what you need and relinquish those resources, the cloud becomes a very attractive proposition. So at the high level, we have the Google Cloud infrastructure. We have what we call cloud compute. But of course, part of what that consists of is the compute engine itself, that is virtual machines, and then app engine, which is the kind of higher level of abstraction where you don't deal with the bare metal. You just deploy your platform to a managed compute resources, your software to manage compute resource, and it just works. So, well, it doesn't just work, but the infrastructure is managed in any case. So we have the other block is the cloud storage. So you have all sorts of storage options from NoSQL to SQL-based and data warehouses and otherwise. And these options scale to handle increasingly humongous data sets. And of interest here is BigQuery, which we'll talk about down the road, for handling analytics workloads. The other component is the big data and analytics component. Okay, now I think BigQuery is under these components, right? So we have BigQuery data flow for handling batch and stream data processing. So if you're getting a data set, if you're using historical data set, data flow will do just well for bringing that into the cloud parameter or moving it around. If you have streaming data sets, probably it's coming from a telemetric device or a couple of sensors and all those kind of stuff. Data flow can handle those kind of workloads with little code modification. And that's the beauty of that infrastructure. And then GCP also has the Cloud AI platform, and this has a couple of APIs for quote-unquote automatic ML. So for some well-known tasks like vision and language, you have APIs and that you could pass in your data set, and it gives you your desired result. And you see some of these APIs in the apps we have on our phones, like Google Translate and otherwise. So those APIs can be leveraged in your software projects. So it's good to know that those stuff are out there. And one other thing I just thought I'll mention is Google Collaboratory. So this is an interactive platform for if you want to go in, get your hands dirty and just model and build stuff, but you don't have a GPU and you don't want to use GCP for some reason, you could have access to, just like you use Google Docs. So you could use this as an interactive notebook interface for writing up Python scripts or TensorFlow and playing around with all those packages at no cost. So this is something I think that we should know about and take advantage of. Okay, so TensorFlow 2.0 and Keras. Now I mentioned this because if you want to actually work with TensorFlow, you need to build on the platform. So you could want to start with Collab or use any other notebook hosted VM on GCP or work on your local machine. Now at a TensorFlow, just to explain the ecosystem, TensorFlow is a really, I call it, of course, it is an ecosystem as opposed to, it's more like it's growing bigger than, it's a package, a Python package, but it does a whole lot. Now we have, from the high level, Keras and estimators. So Keras, now in TensorFlow 2.0, is a first-class citizen and almost like the de facto way in which ML models are developed. And then just what I'll call the mid-level package is things you like layers and data sets and metrics and so on. Now these packages help in building neural network models, as we'll see, and they also encapsulate all sorts of mathematical abstractions, so you don't have to think about them. And something to note here about ML, you can, it's possible, you can apply ML in industry without necessarily knowing the details of the mathematical details. You can apply it really good in the industry. Now there are many details. Sometimes when you read papers, you think you get it, but when you sleep and wake up, you know you don't quite get it. But you can use it to work once you have an idea of what it does and how you can evaluate it, and so on and so forth. You can take these packages and apply it meaningfully to problems you care about. So you don't have to have a PhD to work as a data scientist or in the applied machine learning space. Now the other layer here is the low level. Now this gives you the ability to, build your networks from scratch. So doing all the affine transformations and initializing your weights, and of course how it moves through the layers, the affine transformation, writing your backprop, and coming up with your novel ideas in improving the whole function approximation, how a neural network should learn and capture information about the world. Now, researchers can leverage these low-level tools, but from an applied perspective, you don't have to do it. And you shouldn't even be doing it. You shouldn't be doing it because a lot of engineers and really smart people have come up with these packages that will make life and your business a whole lot easier. So now we'll just talk a bit about the low-level layers, mid-level TensorFlow API, starting with the layers. So let's assume we want to build. Okay, can't see from there. Okay, so let's assume we want to build. Maybe I will hold this in my hand so I would see my.
Pop it out, I think.
Yeah.
There you go.
Okay, that's better. Great. So here we want to build a neural network that has a couple of convolutional layers. Now, don't bother about if you don't know this, what a convolutional layer is, don't bother at all. You have a couple of layers, I'll put it that way, and then you have the idea of these layers is to learn something about the input, something about the data that it's receiving, and the question here is, given a particular output, how can I understand this data so I could learn an abstraction more or less of a real world. So if I see a sample of this data that I did not see when I was learning, I will be able to make an educated approximation of what the output will be like. So the idea is you have an input, you have some learning layers, and then you have an output. So how these layers are built, there are mathematical details to that, but you don't have to bother about it. So you could call a tf.keras.layers method, and you build these layers up, and then you have your output. So just being in an environment where you understand why convolution, what's a convolutional layer? What does it do to your input? And for various types of input, how does it learn from that input? What's the output of a convolutional layer? And what's the max pool layer? What does it do? So that kind of conversational question, like if you have a question-like mindset, you can stepwise analyze things. You can do applied ML. So and packages like the layers package of TensorFlow and the rest will be very helpful as you build your models. The next is the dataset API. So with the dataset, it helps you to build efficient input pipelines. Now this might be important when you are dealing with really large data input and talking about megabytes and so on of records. It just helps you handle the whole underlying memory and all sorts of issues in getting data quickly enough into the model for learning. And it's something we'll leverage a whole lot. Now, there are ways of getting input into the model without passing through the dataset API, but this really makes that process efficient, especially when you want to speed up the training, your ML training phase. And the next briefly is what we call feature columns. Now, it's when you are passing input. Now, again, I will touch, you use this when needed. There are many ways to approach this, but it's something that's out there, and you probably see this more when you're working with estimators. So here you can describe the input that is coming into the estimator model, and so if a particular, let's say you have some tabular data set, and if 3 records are numeric, you want to describe it, you want to tell the model that record column A, B, and C is of numeric type, the rest are categorical, so you should do some sort of transformation with it before it can be used in the model. So it helps in that, and it's yeah. So we will see. We may see an example where this is leveraged, and now let's talk about estimators. Now, estimators is a high-level TensorFlow API. Now, as of now, there are a couple, but estimators and Keras are like the 2 most widely used. Keras is almost like a de facto, is the first choice. I mean, that's my own opinion from how I feel, how I look at my assessment of how TensorFlow is arranging its platform. I think Keras is put out there as the first choice and the go-to for building, for working with TensorFlow. But Estimators is also high up there and used a lot, especially when you want to scale to, you want to have the same model trained on the GPU and trained on the TPU. Estimators is really good for that without changing too much. So in Estimators, we have something called the pre-made estimators. We have some canned classifiers. So if you want to use a trees algorithm or a deep neural network or some linear or logistic classifier, you could take this function calls out of the box, pass in the relevant input, and you get your output. So then you also have what we call custom estimators, where you can build the internals of how you want your classifier to learn. So like just this kind of captures what I said before. You have an input, you have the data, right, and then you have an input function, and you can use FeatureColumns to the FeatureColumns API to describe the data type of your attribute or input attribute, and you pass it into the model, the estimator model, estimator classifier, and then you can train it, evaluate it, and use it to predict. So given an input, can I predict the output? Now, Keras is the other high-level API, and there are two broad classes of ways of working with Keras, either working with the sequential API or the functional API. Now, the sequential API, there's a graph I showed earlier on, where you could, so when you have an idea of your layers, especially when it's a sequence, your neural network is structured as a sequence of layers. The sequential API will be best for that. But if you have a neural network that's a bit more complex, like the architecture is not necessarily sequential, a couple of things are happening, and then you are using their output to combine with another sequence or another layout, you want to use the functional API. So it gives the flexibility for some sort of interesting network architectures. Now, there's the big idea of the Keras model is either you can create a model, either using the sequential or functional API, you compile it, you train it, you evaluate and predict. So the train, evaluate, predict, it maps with what you would do with the estimators. So not too different at high level of how you work with them, but the nuances comes in how you make those function calls and how you prepare the data that goes into it. But then these are concepts that are not overly tough to grasp. And I hope I'm not being biased in saying that, but I believe that ML is accessible for everyone to get involved in and apply them to the problems you care about. So we'll go over building a simple neural network with Keras. So this is for people here who are already in the field, you'll quickly recognize this use case, and it's like the basic example, the hello world of machine learning. So not machine learning, of deep neural networks. The hello world of machine learning is the MNIST data set. Like if you know, if you're familiar with that field, but if not, don't worry about it. It's not a big deal. Okay, so what we want to do is we have a set of inputs. We want to classify. We have a flower data set, and we have a set of attributes of each flower. So given the attributes, can we tell what flower it is? So what we do is we pass those attributes as inputs into the neural network, the first layer of the neural network. The next layer, just call it a hidden layer for all intents and purposes, but it's called hidden layers anyway. Now the next layer learns something. It kind of learns a representation between attributes and the output is the type of flower. So the goal of this is given a set of attributes of a flower, can the network give a prediction with a high level of accuracy that this is the flower? If I see these attributes, I can tell you what flower it is. So that's the problem. That's the use case. So we will go over the steps of you load the data set. You will separate if it's not separated already, the attributes, what you are using to learn, and the output or the target, what you are learning. And then one hot encode. Where did I put that there? Okay, well, but the idea is if an input is non-numeric, there is a process which you can, because at the end of the day, what you're doing in neural network is you're doing basic arithmetic. You are adding and multiplying certain numbers with themselves. So if you hear words like partial differentiation, or hear words like affine transformation, or whatever terms you hear there, which is, of course, that those are the mathematical terms. All you're doing is you're multiplying, adding, or doing some sort of multiplication and addition, back and forth. So at the end of the day, you're playing with real numbers. So if you have an attribute that is categorical, what we call categorical, is like hot or cold. It's an attribute. You have to transform it, or you code it. If statisticians call it your coding, in a way that it still makes sense, but it's now numeric more or less. So you can add and multiply and do whatever the network needs to do under the hood. Okay. So the next is you create the model, which we'll see. We will then use the datasets API to build that input pipeline, and then we'll build, train, and evaluate. So we'll start by importing our relevant packages. Here you see in line 4, you're importing TensorFlow to use it in your code, and Pandas is some package for manipulating, for playing around with data sets. Okay, so what I did here was I just created a variable that held the column names or the attribute names. So I'm going through this, just I'm thinking about building a model. So don't bother about the code, I'm explaining what the code does. So again, and if anyone here is new to, this is a dev event, so I may make a fair assumption everyone is the developer or a programmer, but people here might not necessarily be in development. So coding is just like speaking. You're using language to communicate an idea. So code is the language, it communicates something to the computer, and you're telling the computer what to do. Behind every line of code is an idea. So how I look at reading code is, what's the big idea? And that's sufficient for me to understand what's going on. So if you program in Python and you see a code in Java tomorrow, what's the big idea? So without going into the details, maybe a lambda function or map reduce, what's the big idea? What are you trying to do? And we can get by thinking that way. So from line 5 to 8, I'm loading the training data from some Excel, quote unquote, or CSV, what we call comma separated value, CSV file. So the data you use to train should not be the same data you use to evaluate. So assume I teach a class for a semester and I give examples in the class. During the exam, if I give the exact examples I gave in class, I cannot really evaluate if the students have learned anything, because the code have well memorized and repeated the same thing in the exam. So the idea of learning is to be able to have examples that are similar, so that you take what you have learned and generalize to new examples. And you can say, okay, yeah, you've really learned the concept. You've learned the principle. So that's why we have a training data and a test data set. So in this next slide, between line 1 and 5, we merely separated so taking the train data set and the test data set, separate the features from the target. And the target is just one column, and the features could be a certain number of columns. Now, in general, let me put that out there because this audience might have people who are advanced in this stuff. So and then what we did in 7 and to 9 is what I talked about earlier, the so-called one-hot encoding. Because our data set has yeah, let me not let me to go in there. But yeah, okay, I'll just say briefly, our data set, the target of our data set is categorical. So we want to say this is a flower or not a flower. So I would keep it that way. So we want hot encode the target so that when the neural network does what is called, in case you've heard this before, what is called the softmax, it can get the okay, we can get the probability that a prediction belongs to a particular class. Okay, I think I said it nicely. So if you hear softmax is anywhere, is probabilities. What's the probability that an output belongs to a particular class? And so here in this slide, we used the datasets API to build a pipeline. And what this pipeline is doing is take the dataset, which we call xtrain, shuffle it, and then give us slices, give us samples from that dataset. So shuffling is a simple but very important step to take when you're training. Some datasets, not all, or for the most part, you probably want to shuffle it and add that randomness in there. Now, that may help to, okay, let me just keep it there because there are a lot of times where if you're working with some sort of time series prediction, you necessarily don't shuffle. But this is well, in general, except time series, I don't know what other edge cases you have out there in the wild, but this is something you would do for any other tabular historical data set that one sample does not have a strong, more or less, dependency on the next. But again, let's keep it that way because there are a lot of, in a real world problem, we have to analyze if we have to shuffle or not. And what are the implications of doing that? So, but that's what it is. Okay. Then the next is you create the model. So this is the using Keras now. The rest, the previous steps were basic or quote unquote boilerplate, but fundamental ML pipelines. So this is the deep learning part, or this is the modeling this is the modeling component, but those pipelines, the pre-processing pipelines and all of that fits into this. And if you do that wrongly, we have garbage at this level. So you have called the Keras model. And what we are doing, we are adding a first layer. So you have a model, you created a sequential model. And then in line 5, we are adding certain layers to the model. So here you're adding what's called a dense layer. We may safely skip the details now without loss of generality. And then you're adding another dense layer, and this will be your output. So we called it a softmax. And I briefly explain what a softmax is. When you have a probability, tell me what's the probability that the output belongs to a particular class. So if I have 3 flower output, what's the probability that a particular sample is this flower? And so in the next slide, we build the model. Then we train the model in line 10, and we evaluate in line 13. That's to see how the model performing with samples that the model did not see when it was being trained. Now, what happened in line 4 to 7 is just a plot, more like it's a nicety in Keras to see your network architecture of really what you built in the previous slide in the sequential model. So this is the output of that graph you saw there in between line 5 to 7. So we created the first input, and these are some of the parameters where you have it. The data set has four attributes. That's why you have this here and so on. What's the input, what's the output, and we added a dense layer, and we have a second dense layer as the output layer. So if you have a more complex network, this can be helpful to understand and analyze your deep neural net. So for this, and this is an example using the functional API. So you could swap the same code, not the same, but the same problem. You could swap the sequential for this. So it's similar, you're doing the same thing, but now you have what you call the layers.input method. Again, the data set has four flower attributes that we want to use in learning, or in predicting rather. And then we pass the first layer, the model input, as a property of the next layer. So we created a dense layer and assigned it to X, and then pass model input into that. And then you have a last layer, which I called predict. We also had a dense layer, and then X is being passed into that final layer. So I'm using this in a simple sense, but then you see that flexibility, how you could take one layer and pass it into another. So it doesn't necessarily have to be linear or sequential. You can create more quote unquote dynamic models, or or graphs. And then so you create a Keras model, you compile it, and that's the gist about building ML models with Keras. And today, if you talk about Keras, you are almost in the same breath saying TensorFlow, because it's part of the TensorFlow ecosystem. But you can also use Keras. Now there's a Keras package out there that still exists. Keras was not part of TensorFlow prior to TensorFlow 2.0. So Keras as a package, as a high-level way of building deep neural networks still exists. So you could still use that package and either run it from use TensorFlow as the back end, or use maybe Microsoft MXNet or some other deep learning library at the back end. But for all intents and purposes, we are working here with Keras as part of TensorFlow. So when you hear TensorFlow, especially if you hear TensorFlow 2.0, Keras is just part of that family. So I don't have to say Keras and TensorFlow or go back, except I'm working with Keras without TensorFlow. So one thing just to point out is something called Tensorboard. So it comes with TensorFlow, and it's a way of visually understanding more about your graph. And when the model is training, you can print out or save properties of the model, or statistics or metrics of your model, that helps you to understand more about what you're building and how is it learning, and to debug and to analyze your model. So it's a nice tool for analyzing your learning model. So I'll safely skip this for now, but this is just a code sample of how to visualize, add TensorFlow into Tensorboard into your model. But all I can say is, when you are training the model with the same model fit function, you only add what's called a callback. And the callback has your Tensorboard parameters that points to where the metrics of your model should log, and a couple of details on how you want it to log. So that's the gist of how to add Tensorboard to your Keras model. Okay. Now the next is modeling with estimators. And I'll just pause here to, not to sound like a broken record, but to reiterate I think the goal of this talk is to give the gist about building ML products. So whatever we are seeing here, we can think with it. For sure, there's code behind it. There is some technicality. There is technicality behind it, but I'll be happy if we can leave here with what's the big idea. And I think that's what really matters to to grow more in this area. Now, so estimators, pretty much the same thing. You have an input function, you describe the features coming into the input using the feature columns. You could use a pre-made estimator, and then you train it, evaluate, and predict. So here in lines 10 to 12, you're loading the data set, and we split it into training and testing sets. That's similar. And this is some housekeeping. Preparing the data set, we want to ensure that the attributes, the numeric attributes, are within the same scale. This will help when you are training, especially when you're using some of these optimization algorithms to train. It's easier for the algorithm to learn something. Let me put it that way. I want to keep it sweet. To learn something when the attributes are within the same scale. That means if column A has a scale of the values that are within one, say 1 to 3, for example. If column B has ranges between 1 to 10,000, it's best that you just kind of standardize the data set so that they fall within the same scale without losing information. Okay, so here we create an input function with the dataset API. Same story. You have give me samples, what they call tensor slices. If it is training, shuffle, repeat, and then give me batches, that's samples from the data set. And then now for feature columns, pretty much in this example, all the columns are numeric. So I did a loop and say, hey, all these columns, they are all numeric columns. So store it in an array I call feature columns, which I will pass into the estimator model or classifier. And so that happens in line 8 to 10 when you're training. So you pass in so you call the what I call input function here. That's the same dataset pipeline that we created here called input function. So what we are passing into it is the training dataset, and then when you're evaluating, you're passing the test dataset in lines 12 to 14. And so that's line 12 to 14 is to evaluate the model with samples that the model did not see when training. Okay, and then I'm wrapping up now. Where you have a really large data set and you want to train and evaluate large scale, your local machine might spend a whole month just training, depending on how large your data set is. So you want to leverage a cloud architecture, and then GCP is one of those options, and that's what I'll be talking about. I know we mentioned some of the storage capabilities of GCP, but want to really take note of what you call cloud storage. So it's like a ubiquitous GCP storage mechanism for storing both live and archival data. It's scalable. You can store really large objects and all sorts of objects. When I use the word object, it could be text, audio, video, whatnot. And it's really good. And the next is BigQuery. It's an analytics data warehouse. So it's really, really good for analytics, for analytics purposes. So it's not necessarily transactional, so it does not replace relational databases. So it's a data warehouse, and it's fully managed. So it's, of course, comes to all the perks of scaling and all that, highly available, and scales and all of that. And it's parallel, so it's really, really fast. And except you test it, probably would. The stuff is fast. That's all I can say. So and it has built-in machine learning capabilities, so you can actually run do ML on your data set in BigQuery using a SQL-like language. So I may go out and say ML with SQL because really that's what it is. So, but I won't be talking about that now. But if you know SQL, because really what you put into BigQuery is stable, like the data set is stable like in nature. So you can run, so BigQuery runs with use SQL for the same, reading and so on. But it's not great for updates. Like that's why I said it's not transactional. So yeah, that's it for BigQuery. The next is data flow, which we talked about earlier for batch and stream data processing. Is something you will see a lot being part of your large scale training pipeline. And this components or products will connect one to each other, as we would see in a couple of seconds. Now, the next is what we call cloud machine learning services. So if you have your code, your Keras model or estimators, you're pulling your data, you're transforming your data, doing the large scale data transformation with what now? With data flow, and you're storing it probably you're storing the transformed data on it could be on BigQuery or cloud storage, but let me assume you're storing on BigQuery, or rather cloud storage for this, in this case. You fetch the data from cloud storage into your model for training, and then you have the output is a model. Now that whole training can happen on what we call cloud MLE, machine learning service or machine learning engine, but it's part of what GCP now calls the Google GCP AI platform. So it has this, how I'll put it is large scale machines, parallel distributed and so on, and GPUs are available. That's the beauty, and TPUs. So you train your model there. So something that would take a couple of hours, it's taking literally minutes to train because the stuff is fast, and that's the beauty of the cloud. And then the model can be hosted on the same cloud machine learning service. Now there are many ways of hosting your model for inference as it connects to your downstream application, because a model in and of itself does nothing. It's how, not does nothing, but it's how you integrate it into your product that matters. So, but hosting on cloud ML is one way, machine learning service or engine is one way of hosting your model, and then exposing endpoints to connect it to your software application and APIs and all of that. So this is this graph here explains how cloud ML works, how it takes data from storage and whatever, but I won't go into that details, but I think I've given the big idea of, so when we hear of cloud machine learning service or machine learning engine, we know exactly what it does. And then I close with this. So assuming we want to leverage GCP to model our big data use case. This is a skinny, it's a skinny modeling architecture that one can think of. So you have the raw data. You probably want to bring it into the cloud perimeter, into cloud storage, and then we could use okay. I have ideas coming into my mind, but I'll follow what is here. Now you could move that data into BigQuery, and from BigQuery you can do exploratory data analysis. So if you see number 3, you could spin up a notebook instance, which is some sort of Jupyter interactive programming environment, similar to what you have in Google Colab, and play around, call the data from BigQuery, understand more about the data, just the things data scientists do, to check the variables and do whatever you want to do to explore, and you could quickly prototype your models there, maybe on samples. And when you're ready, you can use data flow to execute your data transformation that you've already sampled and prototyped on your notebook, but on a large scale. So if you're sampling and prototyping, doing some transformation on your data set, you probably want to do it on 20 million records or even 5 million records. You don't want to do that. But you could prepare it on a couple thousands, 6,000, 10,000, depending on your use case. Then when you're ready, you can scale that up and run it on cloud data flow. And then you can store the output of that of the transformed data back on cloud storage. And you train your model on cloud MLE, and you store the model. Anyway, just put it this way: you train your model on cloud MLE, and you can host it on cloud machine learning service and expose endpoints so that your software application, your website, or your mobile APIs, or wherever is the software layer can make calls to the model and say, this is similar attributes, these are a set of attributes, what's the prediction, what's the outcome? And then the model will be able to give a response to that query. So I think that brings me to the end of this. Again, to recap what was my goal at the beginning is we get the big idea of working with TensorFlow, how TensorFlow works in principle, and how we can leverage the cloud to build data products, to build products that are powered with machine learning. And some of the things I mentioned here, not some, all of the things I mentioned were explained in more detail in a book authored by me, which is available for pre-order, but should be out by mid-October or end of October. And it's titled Building, it's titled Building Machine Learning and Deep Learning Models on Google Cloud Platform. It's exhaustive, so we did unwave some of the things I'm unwaving now, just giving the big idea, but if you want to follow it step by step and actually build something and get a feel for building ML models, I think the book is targeted at people who are in the allied sciences or developers. So allied sciences means you're probably in biological or psychology or something, and everybody's talking about ML, and how it can take your work to the next level. How can I leverage it? I think this is something that you benefit from this book, or you're a developer, because I heard a lot of stuff today, Firebase, Angular, and all of that, and you want to infuse you have an idea of how ML can add something sweet to your software application. But when you open the internet, you're seeing math equations. So we can safely bypass most of that and use it to build stuff that you care about. But thank you so much for listening.
I was like, what am I doing? Any questions over here?
How did you get started with machine learning?
Oh, that's a good question. I hope I heard you, and the question was, how do you get started with machine learning? My goodness. Well, what I can say is that treat it as a now there are two ways to get started. You may want to get started from a theoretical perspective, or you want to get started from an applied perspective. Now, from a theoretical perspective, there are lots of courses online that are thorough. Another path would be getting a degree, doing a master's program would be nice. And if one is so interested, go get to a PhD, but that's in research. So it's theoretical. There's actually a lot of math there, and I think it should be respected for what it is. Now, there's also an applied perspective. where the idea has been encapsulated into programming packages. Like today I heard someone mention jQuery and all sorts of things. These are all packages you call. You know what the package is, you have the documentation, you call it and it does something for you. So you could treat machine learning like how you would treat, I want to be careful, but you can treat machine learning for the most part like how you would treat getting started in software development, in building software applications, software development. You have a package. How does this package work? When do I use this model? What should I pass into this model? What should be the output? How do I interpret the output? How do I know that what I'm doing makes sense? So you have algorithms like, say, what if you will probably hear of linear regression, logistic regression, random forest, support vector machine. There is a theoretical aspect to this, but here's how I'm thinking about it. What's about random forest? What does it do? Why is it good? What are its pros? What are its cons? If I take a random forest package from a model, from a package, say from scikit-learn package or from TensorFlow package, how do I pass data into it? Why do I pass data that way? How am I to interpret the results from it and prove to myself, to my boss, or to my prove that the output is sensible? So you see, I'm asking questions. These are questions that can help you demystify. So I'm telling you, for the most part, they are data scientists. They won't tell you the truth. Lead data scientists, senior data scientists, quiz them on the mathematical undertone, they probably would know. But nobody will tell you that. But they know very well how to analyze the packages and get it to work for them. So they tell you, boy, this stuff, it just works. but nobody said, okay, can you show me how do partial differentiation by hand or back propagation by hand? They probably would not. But there are some who could, those who went from a theory perspective, who built some of this stuff with MATLAB or built it with NumPy and really multiplying. They just don't understand how it works. Now, why that is important, you don't need to. Especially when you're starting off. And you can get a job as a data scientist and in your weekends, say, okay, let me understand more about the math behind this magic for fun. Just let me understand it. But when you get to work, you're getting models, you're getting things working. Now, when you also look at it from a business point of view, when you're presenting a solution that works, rarely you're working in an ML team and the data science team is presenting something to the executives. They are not talking about the math behind random forest. Nobody cares about that. But they care that you can take a problem they care about, and you can use this shiny stuff called machine learning, and you can help them drive their market capitalization, solve their business problem. That's what matters. So back to, just to summarize, how do I get started? I'm thinking you're asking the question from an applied perspective. So you probably want to treat it as you would treat software development and ask these questions and not be too bogged down with the math. And I'm pretty sure there are tutorials out there. We could have a offline discussion on some materials I think can be very useful. And probably on another opportunity to talk about the book. This question was the reason why I set out to write this. And I think you would find it useful. Now, forget the fact that I'm an author, but I had a problem I needed to answer. People are saying, how do I start in this? This stuff is important, but I don't know, it's overwhelming. I told myself, yeah, I agree, it was overwhelming for me. I'm going to do something about it. If I did not solve that friction, you let me know. You probably have to rewrite the whole thing. but that's the friction I set out to solve. So, yeah.
Great, thank you. We're running a little bit behind, so I'm gonna have a 5-minute break and then